Hello, in today's video lesson we're going to explore roots of polynomials, but specifically within the context of complex numbers. We studied a little bit about complex numbers, like how to add, subtract, multiply, divide them, how to graph them on an argand diagram, and we've learned a little bit about conjugates. So what we need to know for here is that that is a fact that roots of polynomial equations always come in conjugate pairs if they're complex. Now what I have here is not a root, it is a factor, so we also have to know the relationship between factors and roots. If z plus 2i is a factor of the polynomial, any factors can be set equal to 0 to find the roots. So one of the roots is going to be negative 2i, and again going with the other fact that complex roots always come in conjugate pairs. If z equals negative 2i is one of the roots of my equation, then z equals positive 2i will also be a root of the equation, which can be converted into a factor. In other words, if 2 plus zi, or z plus 2i is a factor, then z minus 2i is also a factor. Multiplying these two factors together gives us z squared plus 4, which should be pretty obvious. If you tried to solve this equation, you would get plus or minus 2i as your solutions, since, yeah. Okay, so to find the third root, the most direct approach would be to use long division, keeping in mind that the 0 holds the place value of the linear position. I won't review the long division algorithm here, but suffice it to say we know we're doing the algorithm correctly if we end up with a 0 remainder, because this has to be a factor. So nonetheless, what we learn is that the third factor is going to be 2z minus 3. Now what I could do to check would be to multiply this back out again, which is semi-redundant. Instead, what I'd like to do is to offer an alternative approach. And this works out in special cases. It's not always the best approach, but it can be a really efficient approach if it's done correctly. When I take z squared plus 4 and multiply it by az plus b, I know I should be getting this polynomial here. And the only two factors that create the constant at the end are the 4 and the number b. So I know that 4b has to equal negative 12, which means b has to be negative 3. So I've got my b value. Here we see right here, b equals negative 3. For a, the only way we're going to get the z to the third, the z cubed factor, would be to multiply the z squared times az. And when you multiply z squared times az and get 2z cubed, that means a has to equal 2, which is again the conclusion that I found right here. Finally, a third approach would be to look at the given polynomial, recognize it's a 4-termer, and try factoring by grouping. Factoring by grouping only works in special cases, but this is actually one of those special cases. So we group the first two and we group the last two, and we look for common factors in the first pair, and we look for common factors in the second pair, and we factor out. In the end, look what we factored. We factored a z squared plus 4 and a 2z minus 3, which means we have all three factors. So 3 different approaches to the same truth. Sometimes the direct approach is the only approach, but in specially created situations we might find some other techniques that could be more efficient if we're aware. Slightly more engaging problem, although it's really direct in its methodology. We have 2 roots for a cubic equation. One of them is a real root and the other is imaginary, which means we already know automatically the third root. Then we just basically have to find out the values of b, c, and d, which means essentially we have to find the polynomial where the a coefficient is 1, and we know the 3 roots. So as simple as identifying the conjugate pairs, we have the 2 given roots plus a conjugate pair. We can convert those into factors, and we can start multiplying them out. Now, specifically here we have z minus a complex number and we have z minus the conjugate. Notice that it's not z plus here and z minus here. We're not taking conjugate factors, we're talking about conjugate roots. So those are the parts that need to be conjugated. And now this particular skill set of multiplying z minus a number times z minus its conjugate, this particular thing is going to happen every time we have questions of this ilk. So it's so it could be beneficial to actually get good at multiplying this out without having to do all long form. So what we should have is, this is the long form way. We're going to have z squared minus the first root times z minus the conjugate root times z plus the product of the conjugates. Now in the section on conjugates, we learned some properties of conjugates. If we multiply two conjugate pairs, we get the square of the magnitude of the original given number. And if we add two conjugates together, because the imaginary parts are opposites, they will drop out, and we just get twice the real part if we add two conjugates together. So that we discovered in the last chapter. We're going to apply that here so that we can make our work a lot easier, so that we can go from conjugate factor, or sorry, two pairs of factors and easily multiply them all out. But don't forget that z plus 2, that real factor in there too. Anyway, so the first term is z squared, obviously, and then what we're going to have for our second part is minus twice the real part, and then we're going to take the magnitude of z squared, which is just basically 4 plus 9, which is the 13 that I get right here. So using those shortcut facts, we don't have to perseverate over all this, and then we again have to multiply the result by z plus 2. This is straight up algebra 2 kind of stuff. Just FOIL it all out and collect like terms, and we're golden. So b equals, b equals -2, c equals 5, and d equals 26, because we were asked to find b, c, and d. So I first find the polynomial and then indicate the numbers that I need. So here is that statement that I shared with you. It's from, it's in your textbook. If you multiply z minus a conjugate, a complex number, and x minus a complex number times x minus its conjugate, then we can quickly FOIL it out by saying, well, the first term is going to be x squared, second term is going to be -2 times the real part of z, and the third term is going to be the square of the magnitude. So if you can get good at that, it's going to save you a lot of effort, any valuable moments on an IB exam. All right, so for the last one we're going to explore here, we've got a quartic equation, and it's got real coefficients, and they gave me 2 of the 4 roots. I know there's going to be 4 roots. Fundamental theorem of algebra says quartics are going to have 4 roots. We get 2 of them. Since they're both complex, we know then that conjugate pairs are going to make up the other 2 roots. So we have now 4 roots. We convert them into 4 factors, and we multiply those factors together. So this is the same skill that we observed in the last set, multiplying z. Well, this part's easy, but this part right here, z minus a number, z minus its conjugate pair. Again, take the z squared, we take the twice the real part of z, and we add the square of the magnitude. The rest of this, again, is just a skills drill. But it's easy to make a lot of mistakes. You could drop negatives, do all sorts of crazy stuff. As a matter of fact, here we can see that I actually turned a negative into a positive somehow, inexplicably. So get rid of that. Problem solved. And just to point out here, I was able to put the equation into Wolfram alpha and verify, first of all, the plot itself shows a graph, a polynomial that never reaches the x-axis, and furthermore, Wolfram is kind enough to give me all 4 of the solutions, and those are the 2 of the given solutions plus their conjugate pairs. Hope you found this helpful. Have a great day.